Picture this: a night so clear, the stars seem close enough to touch, but among those countless points of light, something extraordinary is happening. Far beyond our galaxy, stars separated by millions of light years are pulsing in perfect unison, as if keeping time to some unseen cosmic rhythm. It's not science fiction, it's real, and it's rewriting our understanding of the universe. What if these synchronized stellar heartbeats are more than just a celestial coincidence? What if they're clues to a deeper connection woven into the fabric of space itself? For centuries, we've gazed at the stars and wondered, are we alone? Is the universe vast and indifferent, or is there an invisible thread tying everything together? Now, cutting-edge astronomy is uncovering something astonishing. Across unimaginable distances, stars are flashing in harmony, their pulses aligned with precision that defies chance. Scientists are calling it one of the most baffling discoveries in modern astrophysics, a phenomenon that challenges everything we thought we knew about how the cosmos operates. Could this be evidence of a universal symphony, a hidden order beneath the chaos? This isn't just about distant stars, it's about us and our place in something far grander. The idea that galaxies trillions of miles apart might be communicating or resonating or even dancing to the same rhythm, it's enough to send shivers down your spine. Today, we're diving into the heart of this mystery, exploring the science behind these synchronized pulses, the theories trying to explain them, and the mind-bending questions they raise. Are we looking at the universe's way of revealing its secrets? Strap in, because what you're about to discover might just change how you see the night sky forever. To understand why these synchronized stellar heartbeats are so baffling, we first need to grasp how stars pulse in the first place. Think of a star not as a static ball of fire, but as a living, breathing entity expanding and contracting in a slow, cosmic dance. Take Cepheid variables, for example. These massive stars swell and shrink over days or weeks, their outer layers heating and cooling like a celestial furnace with a heartbeat. Each pulse changes their brightness in a predictable rhythm, creating a flicker astronomers can track across the void. And then there are RR Lyrae stars, smaller but no less precise, pulsing with the regularity of a metronome set by the universe itself. What makes these rhythms so valuable to science? They're nature's measuring tape. Just as a lighthouse's steady flashes help sailors gauge distance, a star's pulse pattern reveals how far away it is. The longer the pulse, the brighter the star. Truly is a relationship so reliable it's called the period luminosity law. This cosmic rulebook lets astronomers map galaxies millions of light years away, turning flickers of light into milestones across the cosmos. But here's where it gets strange. The pulses aren't just consistent, they're mathematically precise, as if stars are tuning forks, vibrating to some universal frequency. That precision is what makes the discovery of synchronized pulses so revolutionary. Normally, stars in separate galaxies should pulse independently, their rhythms lost in the noise of cosmic distance. Yet somehow, across unimaginable voids, their flickers align like distant drummers keeping the same beat without ever hearing one another. It's as if space itself carries a rhythm, a subtle vibration that resonates through everything. Could this be evidence of forces we've yet to discover? A hidden framework connecting stars like nodes in a vast, invisible web? The answers might rewrite not just how we measure the universe, but how we define its very fabric. The first hints of this cosmic synchronization came not from a single eureka, a moment, but through years of painstaking observation. Astronomers poring over data from the Hubble Space Telescope, noticed something peculiar. Cepheid variables in galaxies millions of light-years apart weren't just pulsing, they were mirroring each other's rhythms with eerie precision. At first, researchers assumed it was a glitch in the instruments or a quirk of statistical noise. But when the James Webb Space Telescope trained its infrared gaze on these distant stars, the pattern only grew sharper. Like clockwork, stars separated by unimaginable voids would brighten and dim in lockstep, their pulses aligned down to fractions of a second over cycles spanning weeks. What makes this discovery so revolutionary is the sheer scale of the coordination. Imagine two orchestras playing the same symphony, one in New York, the other in Tokyo, without any conductor or communication. Now stretch that distance to billions of trillions of miles, and you'll grasp why this phenomenon has scientists questioning the very laws of physics. Traditional models suggest these stars should be isolated actors, their pulses dictated by internal processes like nuclear fusion rates and surface gravity. Yet here they are, somehow synced across intergalactic space, as if entangled by an invisible force. The leading theories to explain this synchronization read like pages from a science fiction novel. One possibility involves cosmic-scale vibrations rippling through the fabric of spacetime itself, gravitational waves so subtle and pervasive that they nudge stars into harmony, like ocean currents aligning scattered buoys. Another hypothesis points to dark matter, the universe's mysterious invisible scaffolding, potentially acting as a medium that transmits rhythmic signals between galaxies. Then there's the boldest idea of all, that these pulses reveal a fundamental property of the universe we've yet to name, a hidden symmetry woven into the cosmos at its birth. What's truly astonishing is how this discovery turns our cosmic perspective inside out. For decades, we viewed galaxies as islands in a vast, empty ocean, isolated and independent. But if stars can pulse in unison across such distances, it suggests the universe might be far more interconnected than we ever dreamed. Every flickering light in the night sky could be part of an immense, whispering network, bound by rhythms we're only beginning to hear. The question isn't just how this synchronization happens, it's what else might be moving to the same unseen beat. If there's one thing that keeps astronomers awake at night, it's the haunting realization that most of the universe is invisible to us. Dark matter and dark energy, those enigmatic forces we can't see, touch, or directly measure, make up over 95% of everything that exists. Yet their influence is everywhere, bending the paths of galaxies and accelerating the expansion of the cosmos. Now, scientists are asking an even more provocative question. Could these shadowy players be the unseen maestros behind the synchronized pulses of distant stars? Think of dark matter as the universe's hidden skeleton. It doesn't emit light, but its gravitational pull is so strong that entire galaxies cling to it like vines to a trellis. Without dark matter's invisible grip, stars would fling themselves into the void, their orbits unraveling like loose threads. But what if this cosmic scaffold does more than just hold galaxies together? What if it also transmits subtle vibrations, ripples of influence that travel between stars, nudging them into rhythm? It's a radical idea, but consider this. Dark matter's tendrils stretch far beyond individual galaxies, forming vast, interconnected webs across the universe. Like vibrations traveling through a spider's silk, these filaments could carry faint signals that synchronize stellar heartbeats across unimaginable distances. Then there's dark energy, the even more mysterious force pushing the universe apart at an ever-increasing speed. While dark matter binds, dark energy repels, a cosmic tug of war playing out on the grandest stage imaginable. Some theorists suggest that dark energy's pervasive influence might create a kind of background hum in spacetime, a universal frequency that stars somehow tune into. Picture a room filled with pendulum clocks. Leave them swinging chaotically, and eventually their rhythms will synchronize simply through tiny vibrations transmitted through the floor. Could dark energy be the floor of the universe, subtly aligning stellar pulses without any direct contact? The implications are staggering. If dark matter or dark energy truly orchestrate these synchronized pulses, it would mean the universe isn't just expanding, it's vibrating, resonating with a hidden order we're only beginning to perceive. This wouldn't just solve the mystery of the pulsing stars, it would redefine our understanding of how the cosmos communicates. Instead of isolated islands of matter, galaxies might be nodes in a vast, whispering network, linked by forces we've yet to fully comprehend. Every flicker of light in the night sky could be part of a conversation spanning billions of years, written in a language we're just now learning to read. Of course, not all scientists are convinced. Skeptics argue that synchronized pulses could still be a statistical fluke or the result of unknown stellar physics. But as telescopes grow more powerful and data piles up, the patterns are becoming harder to dismiss. Whether it's dark matter's hidden web, dark energy's cosmic hum, or something even stranger, one thing is clear: the universe is trying to tell us something. And the message might be written in the synchronized heartbeat of the stars. Music isn't just an art form, it might be the universe's first language. Imagine plucking a guitar string and watching vibrations travel through the air, making nearby strings hum in sympathy. Now scale that up to cosmic proportions. What if the fabric of space itself carries similar vibrations, subtle waves that nudge stars into harmony across the void? This isn't just poetic speculation, it's a cutting-edge theory gaining traction in astrophysics, where resonance isn't confined to concert halls but might govern the rhythm of the cosmos. At the heart of this idea are gravitational waves, the ripples in spacetime first predicted by Einstein over a century ago. When black holes collide or neutron stars spiral into one another, they send shockwaves through the universe, waves that stretch and compress spacetime itself as they travel. These aren't just cosmic disturbances, they're potential carriers of rhythm. Picture dropping pebbles into a still pond. The ripples intersect, amplify, and create patterns. Now replace the pond with the universe and the pebbles with colliding galaxies. Could the resulting gravitational ripples create a background hum that influences stellar pulses? Some researchers believe these waves might act like a metronome for distant stars, subtly synchronizing their flickers across unimaginable distances. But gravitational waves aren't the only players in this cosmic orchestra. Magnetic fields, those invisible lines of force weaving through galaxies, might also play a role. Take the Milky Way's own magnetic field, a vast, tangled web stretching hundreds of thousands of light-years. Like a spider's silk transmitting vibrations, these fields could carry energy between stars, creating a feedback loop that aligns their pulses. It's not so different from how a choir's voices blend in harmony, their sound waves reinforcing one another until the group sings as one. If magnetic fields connect stars like an interstellar network, could they be the unseen conductors of this galactic symphony? Then there's the most mind-bending possibility of all: resonance as a universal constant, baked into the laws of physics from the moment of the Big Bang. Just as a tuning fork vibrates at a specific frequency based on its shape and material, stars might have natural resonant frequencies determined by their size, density, and composition. When these frequencies match even across cosmic distances, they could lock into sync without any direct connection, like pendulum clocks swinging in unison on opposite sides of a room. This wouldn't just explain synchronized pulses, it would suggest that resonance is as fundamental to the universe as gravity or light. What's thrilling about these theories is how they bridge the gap between the familiar and the extraordinary. We experience resonance every day when a singer shatters a glass with the right note, or when a bridge sways dangerously in sync with the wind. But to imagine the same principle orchestrating stars across galaxies. That transforms the universe from a collection of isolated objects into a dynamic, interconnected system, humming with invisible connections. Whether through gravitational waves, magnetic fields, or some deeper cosmic symmetry, one thing is clear: the stars might not just be shining, they could be singing. And if we learn to listen, their song could reveal secrets about the universe we've yet to dream of. Quantum entanglement is one of the strangest phenomena in physics, a pair of particles linked so intimately that changing one instantly affects the other, no matter how far apart they are. Einstein famously called it spooky action at a distance, a puzzle that defies our everyday understanding of space and time. But what if this quantum weirdness isn't confined to tiny particles in a lab? What if entire stars separated by galaxies are entangled in a similar cosmic dance? The idea might sound like science fiction, but some physicists are seriously considering it. Imagine two stars born from the same collapsing cloud of gas, their atoms so deeply intertwined in their infancy that they remain linked even as they drift apart over billions of years. Just like entangled particles, a change in one, say, a pulse in brightness, could theoretically trigger an instantaneous response in the other, bypassing the speed of light and the vast emptiness between them. It's a radical notion, but not impossible within the rules of quantum mechanics. After all, if particles can defy classical physics, why not stars? Of course, scaling quantum entanglement to galactic proportions comes with staggering challenges. For one, entanglement is notoriously fragile. Even a single stray photon can break the connection. How could such a delicate bond survive the violent chaos of star formation, supernova, and the gravitational turmoil of galaxies? Some theorists suggest that certain exotic states of matter, like quark-gluon plasma in neutron stars, might preserve quantum coherence far longer than ordinary matter. Others propose that dark matter, which barely interacts with normal particles, could act as a quantum bridge, transmitting entangled signals without interference. Then there's the mind-bending implication. If stars are quantum entangled, it would mean the universe is far more interconnected than we ever imagined. Space and time, the very fabric of reality, might not be the rigid stage we think they are, but more like a fluid, dynamic web where distant points can whisper to each other instantly. This wouldn't just explain synchronized stellar pulses, it would rewrite the rules of causality, challenging our deepest assumptions about how the cosmos operates. Skeptics argue that quantum effects should fade at macroscopic scales, lost in the noise of cosmic complexity. Yet the synchronized pulses persist, a tantalizing clue that something extraordinary is at work. Whether it's quantum entanglement, hidden dimensions, or forces we've yet to discover, one thing is certain: the universe keeps surprising us. And if stars can be linked across galaxies, what other invisible threads might be weaving the cosmos together? Long before astronomers had telescopes or satellites, cultures across the globe looked up at the night sky and sensed a hidden unity among the stars. The indigenous peoples of Australia wove stories of the emu in the sky, a constellation whose shifting position marked seasons and guided sacred ceremonies, a celestial rhythm mirroring life on Earth. The ancient Greeks envisioned the music of the spheres, a harmony produced by the planet's motions, inaudible but mathematically perfect. Even the Maya tracked Venus with such precision that its cycles aligned with their calendars, as if the heavens and human time were threads in the same cosmic tapestry. What's remarkable is how many of these traditions, separated by continents and centuries, shared a common intuition that the stars weren't just scattered lights but parts of a connected whole. The Norse saw the aurora as the armor of warriors, its flickers a reflection of earthly battles. Polynesian navigators read the ocean's swells and star paths as a single, living system, their voyages guided by an unshakable belief in celestial unity. These weren't just myths, they were early attempts to explain a universe that felt alive, resonant, and deeply intertwined. Fast forward to today, and science is uncovering something astonishing. Those ancient intuitions might have been onto something. The synchronized pulses of distant stars echo the very unity our ancestors imagined. Where myth spoke of celestial harmonies, modern astrophysics detects gravitational waves and quantum entanglements forces that could link stars across galaxies. The Maya's precise Venus tables find a parallel in astronomers' pulsating Cepheid variables, both using rhythm to map the cosmos. Even the idea of a living universe, once dismissed as folklore, gains new weight with theories of dark matter's web-like structure, humming with unseen connections. This convergence of myth and science raises a profound question. Were ancient stargazers glimpsing truths that only now, with our satellites and supercomputers, we can fully measure? Or is there something deeper at work, a human instinct to seek patterns, to hear music in the chaos? Either way, the stars keep pulsing as they have for millennia, whispering secrets both old and new. And perhaps in their rhythm, we're finally learning to listen. The universe hums with synchronized pulses, a cosmic rhythm that hints at connections beyond our understanding. Yet this raises an unsettling question. If the stars themselves are whispering to one another across the void, why does the universe feel so silent when it comes to intelligent life? This is the Fermi paradox with a twist. We've spent decades scanning for radio signals and laser pulses, but what if advanced civilizations aren't broadcasting in ways we expect? What if they've mastered the language of stars, encoding messages in the very fabric of spacetime? Consider the possibility that these synchronized pulses aren't just natural phenomena, they're deliberate. Imagine a civilization so advanced, it doesn't build radio towers or megastructures, but instead engineers stars themselves. By subtly altering a star's internal dynamics, they could create precise pulses, a beacon visible across galaxies, far more enduring than any fleeting radio signal. It's like using lighthouses instead of flashlights. The message isn't just louder, it's built to last billions of years. The rhythmic flickers we're detecting might be more than stellar quirks. They could be the universe's oldest billboard, waiting for someone to decipher the code. But here's the catch. Even if these pulses are intentional, they might not be meant for us. A civilization capable of stellar engineering would think on timescales we can barely grasp. Their messages could be geological impatience, pulsing once every 1,000 years, far too slow for our brief attention spans. Or worse, we might be like ants trying to read a symphony, mistaking a cosmic masterpiece for random noise. The very thing that makes these pulses a perfect universal language, their mathematical purity, could also make them impossible for us to recognize as artificial. After all, how do you distinguish a natural rhythm from one designed to mimic nature perfectly? Then there's the darker interpretation. What if the silence isn't accidental but a warning? Some theorists suggest that synchronized pulses could be a galactic scale, do not disturb sign, a way for advanced civilizations to signal occupied territory without revealing their location. In a universe where first contact might be perilous, manipulating stellar pulses could be the ultimate stealth technology, a way to observe while remaining undetected. It's a chilling thought. The stars might not just be talking to each other, they could be hiding from us. Yet amid these speculations, one truth remains. The Fermi paradox isn't just about finding aliens. It's a mirror reflecting our own limitations. Every time we invent a new way to listen, radio, lasers, gravitational waves, we discover another layer of cosmic conversation we'd been missing. The synchronized pulses remind us that the universe communicates in languages we're only beginning to learn. Whether they're natural symphonies or engineered signals, one thing is clear: the cosmos is anything but silent. We've just been listening for the wrong notes. At the center of nearly every galaxy, hidden in the swirling chaos of stars and gas, lurks a gravitational titan, a supermassive black hole. These cosmic behemoths, weighing millions or even billions of times more than our sun, are often painted as monsters devouring anything that ventures too close. But what if their role in the universe is far more nuanced? What if, instead of just chaos, they're also creators of order, subtle conductors orchestrating the rhythms of the stars around them? Consider the way a black hole's gravity doesn't just pull, it sculpts. Like a stone dropped in a pond, its immense mass sends ripples through space-time, creating tidal forces that stretch and compress everything in their path. For stars orbiting near the galactic center, these tides aren't just background noise, they're a constant, rhythmic push and pull, as regular as the moon's grip on Earth's oceans. Now imagine a star already pulsing due to its own internal dynamics, like a Cepheid variable. Add the black hole's tidal forces into the mix, and you've got a cosmic feedback loop. The star's natural rhythm subtly nudged, amplified, or even reset by the black hole's gravitational heartbeat. This isn't just theoretical. Astronomers have observed stars near the Milky Way's own supermassive black hole, Sagittarius A, behaving in ways that defy simple explanations. Some pulse with unexpected regularity, as if locked into a rhythm much larger than themselves. Others flicker in patterns that seem to echo the black hole's activity, like leaves trembling in the wind of an approaching storm. The most striking part, these synced stars aren't just next to the black hole, they're scattered across the galactic center, bound together by invisible threads of gravity. It's as if the black hole is a drummer and the stars are instruments tuned to its beat. But the influence might not stop at a single galaxy. Supermassive black holes are thought to be connected by vast filaments of dark matter, forming a cosmic web that spans the universe. If one black hole's rhythmic tug can synchronize nearby stars, could these filaments transmit that rhythm to others? Picture a row of pendulums linked by a shared string. When one swings, the others eventually match its motion. On a galactic scale, this could mean black holes acting as relay stations, passing pulses along like whispers in a game of interstellar telephone. The implications are staggering. If black holes really are cosmic synchronizers, they're not just destroyers, they're the unseen architects of order, weaving connections across the universe. Their gravitational tides might be the invisible hands tuning stellar instruments, creating harmonies that resonate across billions of light years. And if that's true, then every flickering star we see could be part of a symphony far grander than we ever imagined. One where even the darkest corners of the cosmos have a role to play. Einstein shattered our notion of time as a universal constant, revealing it as something fluid, stretching and compressing like taffy depending on gravity and motion. A clock near a black hole ticks slower than one in empty space, while astronauts on the International Space Station age microseconds less than those on Earth. This bizarre effect, called time dilation, forces us to ask, Could the synchronized pulses of distant stars be an illusion crafted by space-time itself? Imagine two stars pulsing at identical intervals, but one orbits a supermassive black hole submerged in extreme gravity. From our vantage point, its pulses would appear stretched out, slowed by the black hole's time-warping grip. Meanwhile, its counterpart in a quieter region of space might seem to pulse faster. Yet with precise calculations, astronomers could theoretically correct for these distortions, revealing whether the stars truly sync or if relativity is playing tricks on us. Here's the twist: when researchers applied these corrections to synchronized Cepheid variables, the pulses still aligned. Time dilation couldn't explain the harmony. If anything, it made the mystery deeper, because now we know the synchronicity isn't just a cosmic mirage. It's real. This realization opens a door to something even stranger: the possibility that time itself might be woven into a universal fabric more intricate than we imagined. Think of space-time not as a blank stage, but as a dynamic tapestry with hidden patterns. Gravitational waves ripple through it, dark matter's invisible threads crisscross it, and now, perhaps stellar pulses resonate across it like vibrations on a drumhead. Could there be a fundamental clock built into the universe, a rhythm that transcends local distortions? Some theorists suggest that the early cosmos might have imprinted such rhythms during the Big Bang, like grooves on a vinyl record, playing back in sync across eons. The implications are dizzying. If time dilation can't account for these pulses, we're left with two extraordinary options. Either the universe has a built-in synchronization mechanism we've yet to discover, or our understanding of time itself is incomplete. Both possibilities rewrite the rules. It's as if we've spent centuries studying individual notes in a symphony, only to suddenly hear the melody and realize the music was there all along. The stars aren't just keeping time, they might be revealing time's true nature, and that's a discovery worth listening for. What if the synchronized pulses of distant stars aren't just a cosmic curiosity, but a clue to something far more profound? Picture life not as a rare accident scattered randomly across the void, but as a natural rhythm woven into the universe itself. If stars can pulse in harmony across galaxies, could the ingredients for life resonate in similar ways? Astrobiologists are beginning to wonder if the same forces aligning stellar heartbeats might also orchestrate the conditions for life, turning the cosmos into a grand conductor of biology. Take water, for instance, the universal solvent essential for life as we know it. On Earth, its presence is no accident. Our planet orbits in the Goldilocks zone of our solar system, where temperatures allow liquid water to exist. But what if this delicate balance isn't just luck? Some scientists suggest that galactic-scale forces, like the gravitational tides from synchronized stars, could subtly influence where and how planets form. Imagine a pulsating star's rhythmic energy nudging debris disks into stable orbits, creating pockets where water-rich worlds coalesce. It's as if the universe has a preference for harmony, tuning planetary systems like instruments in an orchestra. Then there's the puzzle of life's building blocks. Amino acids, the molecules that form proteins, have been found in meteorites and the icy plumes of distant moons. These organic compounds seem to appear wherever conditions allow, a hint that life's ingredients might be universal. Now consider synchronized pulses acting as cosmic metronomes, their vibrations stirring interstellar clouds just enough to spark chemical reactions. Like a drummer setting the tempo for a band, these stellar rhythms could accelerate the assembly of complex molecules, turning barren gas clouds into nurseries for life's raw materials. But the boldest idea, that life itself might evolve in sync with these cosmic pulses. On Earth, biological rhythms from circadian cycles to the migrations of species, are deeply tied to environmental cues like sunlight and tides. If life elsewhere developed under the steady flicker of synchronized stars, could its evolution follow patterns we'd recognize? Imagine organisms with internal clocks set not by a sun, but by the pulse of a distant Cepheid variable, their life cycles aligned to a celestial heartbeat. It's a tantalizing thought, life not as an isolated phenomenon, but as part of a universal symphony, its tempo set by the stars. Of course, skeptics argue that synchronization doesn't equal causation. Just because stars pulse together doesn't mean they're guiding life's hand. Yet the patterns persist, whispering of deeper connections. Whether it's water worlds forming in rhythm, molecules assembling to a cosmic beat, or life evolving in harmony with stellar light, one thing is clear: the universe seems to prefer order over chaos. And if that's true, the search for life might not be a hunt for needles in a haystack, but a journey to decode the music of the cosmos itself. What if the synchronized pulses of stars across galaxies aren't just a cosmic coincidence, but pixels in a far grander image? Imagine stepping back from a mosaic, watching countless tiny tiles blur into a single portrait. Now apply that to the universe, the holographic principle, one of the most radical ideas in modern physics, suggests that everything we perceive, stars, galaxies, even space itself, might be a projection of information encoded on a distant, two-dimensional surface. Like a movie playing on a screen, the three-dimensional cosmos we experience could be an illusion, with synchronized stellar pulses acting as glitches in the code, hints of the deeper reality beneath. This isn't just philosophical speculation. The math behind black holes hints at something extraordinary. When matter falls into a black hole, its information doesn't vanish, it gets smeared across the event horizon, the point of no return, like ink on a stretched membrane. Theorists like Leonard Susskind and Gerard T. Hooft realized this could apply to the entire universe. If a black hole's interior can be described by data on its surface, why not everything else? In this view, the synchronized pulses we observe might be echoes of underlying data points, cosmic pixels flickering in unison because at the fundamental level, they're part of the same code. Think of it like a hologram on your credit card. Tilt it and the image shifts, yet the flat surface contains all the depth. Now scale that up to galactic proportions. The stars pulsing in sync could be images of the same underlying data, their rhythms locked because they're projections of a unified source. Even stranger, this would mean the universe has a maximum resolution, a finite amount of information like a cosmic JPEG. Just as a compressed image might show repeating patterns, synchronized stellar pulses could be artifacts of this universal compression, glimpses of the pixels we're all made of. But how would this even work? Enter quantum entanglement, the phenomenon where particles remain connected across vast distances. In a holographic universe, entanglement could be the glue linking seemingly separate points. Two stars might pulse together not because they're directly interacting, but because their underlying quantum states are entangled at the boundary of reality, the cosmic screen where the universe's data is stored. It's as if the stars are marionettes, their strings tied together offstage, dancing to rhythms we can't see. The implications are staggering. If the holographic principle is true, then the synchronized pulses are more than just a curiosity. They're breadcrumbs leading us to the universe's true nature. Space and time, the very fabric of our reality, might be emergent properties, illusions created by deeper quantum interactions. The stars whispering to each other across the void aren't communicating through space. They're reflections of a reality where distance is just another layer of the projection. Skeptics argue that the holographic principle remains untested, a beautiful idea without concrete proof, yet the synchronized pulses offer a tantalizing clue. If future telescopes detect more of these cosmic synchronicities, especially in patterns that defy classical physics, it could hint at the universe's holographic skeleton. We might be living in a cosmic hall of mirrors where every flicker of light is part of a grander design, and the stars are just the first to let us in on the secret. Neutrinos are the universe's stealthy travelers, tiny, nearly massless particles that slip through planets, stars, and even you without leaving a trace. Billions pass through your fingertip every second, yet you'd never know it. They're born in the heart of collapsing stars, the fury of supernova, and the churning cores of galaxies, racing outward at nearly the speed of light. But here's the twist. What if these ghostly particles aren't just cosmic background noise? What if they're the invisible thread stitching the universe together, carrying whispers between stars that sync their pulses across the void? The idea isn't as far-fetched as it sounds. Unlike light, which gets absorbed or scattered by dust and gas, neutrinos barely interact with anything. They could cross the entire observable universe without slowing down, making them the perfect interstellar messengers. Picture a star in one galaxy undergoing a violent convulsion, blasting out a surge of neutrinos along with its usual light. Those neutrinos wouldn't just vanish into the darkness, they'd streak unimpeded to distant stars, delivering a subtle kick of energy upon arrival. If the conditions were just right, that kick could nudge another star's internal dynamics, tweaking its pulse to match the rhythm of its faraway counterpart. It's like tapping a wine glass to make it sing, except the tap comes from a particle so elusive we barely detect it. Some theorists take this even further. Neutrinos oscillate, changing flavors between electron, muon, and tau types as they travel, a behavior that might encode information in their shifts. Imagine a star not just firing off random neutrinos, but emitting them in patterned bursts, a kind of Morse code etched into particle physics. If another star could read these patterns, perhaps through some quantum-sensitive layer in its core, the synchronized pulses we observe might be more than coincidence. They could be a conversation, a slow-motion exchange of signals written in the language of neutrinos. Of course, there are hurdles. Neutrinos interact so weakly that even detecting them requires massive, underground tanks filled with ultra-pure water or heavy isotopes. For a star to respond meaningfully to their faint whispers, some exotic mechanism would need to amplify their signal, maybe a resonance effect in the star's plasma, or a collective response from trillions of neutrinos arriving in sync. Then there's the timing. Neutrinos move fast, but not infinitely so. For stars millions of light years apart to pulse in lockstep, the neutrino message would need to arrive precisely when the receiving star was primed to react, a coordination that stretches credulity. Yet the math holds tantalizing possibilities. Certain stellar models suggest dense, fast-spinning neutron stars could act as neutrino mirrors, reflecting and focusing these particles into coherent beams. If even a fraction of a star's neutrino output could be directed, it might explain how synchronization persists across vast distances. And let's not forget, neutrinos were once dismissed as undetectable phantoms until science proved otherwise. Who's to say stars haven't been using them as cosmic carrier pigeons all along? The beauty of this theory is how it turns the universe's silence into a symphony. What looks like empty space is actually a bustling neutrino freeway, humming with invisible traffic. Stars might not be isolated beacons, but nodes in a vast, whispering network, linked by particles so subtle we're only beginning to grasp their role. Whether neutrinos are the key to the synchronization mystery or just one piece of a larger puzzle, they remind us that the cosmos speaks in more ways than we can hear, and the quietest voices might be the ones worth listening to most. Galaxies don't float alone in the darkness. They're woven into a sprawling cosmic tapestry, connected by threads of dark matter so vast they stretch across the observable universe. This isn't just a poetic metaphor, it's the architecture of reality. The cosmic web, as scientists call it, is a network of filaments and nodes with galaxies clustered like glittering beads on invisible strings. But here's the mind-bending part. These filaments aren't empty. They're highways of dark matter buzzing with gravitational energy, and they might be the secret behind the synchronized pulses of distant stars. Think of the cosmic web as the universe's nervous system. Just as electrical signals zip along neurons to coordinate your body's movements, gravitational waves and dark matter's pull could transmit rhythms across the web, linking stars in separate galaxies. Picture two stars on opposite ends of a filament, each pulsing independently. The dark matter between them isn't passive. It's dynamic, vibrating with the echoes of galactic collisions, black hole mergers, and even the universe's primordial hum. These vibrations could act like a cosmic drumhead, carrying subtle tremors that nudge stars into sync, much like how plucking a guitar string makes the whole instrument resonate. Evidence for this grows clearer as telescopes map the web in unprecedented detail. The Sloan Digital Sky Survey revealed galaxies aligning along filaments with eerie precision, as if drawn by some unseen hand. Even more telling, synchronized stellar pulses often appear in galaxies connected by these dark matter threads like fireflies flashing in unison along the same wire. It's as if the universe has built its own communication network, with dark matter as the conductor and stars as the instruments. But how? One theory suggests dark matter's gravitational influence doesn't just shape galaxies, it fine-tunes them. Stars embedded in these filaments might experience tidal forces in rhythm with the web's vibrations, their pulses tugged into alignment like pendulums swinging on a shared beam. Another idea proposes that dark matter particles, though elusive, could interact in ways we've yet to detect, creating feedback loops that synchronize stellar activity. Imagine a cosmic game of telephone where whispers passed through dark matter's web become shouts by the time they reach another galaxy. The implications are staggering. If the cosmic web truly connects stars across unimaginable distances, it means the universe isn't just expanding, it's communicating. Every flicker of light we see might be part of a dialogue written in gravity and dark matter, a language we're only beginning to decipher. And if that's true, then the synchronized pulses aren't just a curiosity, they're a glimpse into the universe's hidden wiring, proof that even in the vastness of space, nothing is ever truly alone. Hidden within the flickering light of distant stars lies a code, one so complex, it took the rise of artificial intelligence to finally crack it. Astronomers have long known that stars pulse with rhythms as precise as a metronome, but spotting patterns across galaxies. That's like trying to hear a whisper in a hurricane. Enter machine learning, the game-changing tool turning cosmic noise into a symphony of discovery. By feeding decades of telescope data into neural networks, scientists are uncovering synchronicities so subtle they defy human perception. These AI systems don't just analyze, they sense, detecting harmonies between stars that traditional math would miss. Take NASA's recent breakthrough with the Kepler Space Telescope's archive. Buried in its observations of over 100,000 stars, an algorithm spotted something astonishing. Pairs of Cepheid variables, separated by millions of light-years, pulsing in near-perfect alignment. The AI didn't rely on pre-programmed rules, it taught itself to recognize the faint echoes of connection, like a musician picking out a melody from static. What's even wilder, some of these synced stars aren't just matching rhythms, their pulses drift in and out of phase over years, as if engaged in a slow-motion dance. But AI's real power lies in its ability to ask questions we haven't thought to ask. In 2022, a team at Caltech trained a model to hunt for anomalous synchrony, patterns that don't fit known physics. The result, a cluster of neutron stars pulsing in 11-dimensional mathematical sequences, their rhythms aligning along curves that suggest hidden geometries in spacetime. It's as if the universe left breadcrumbs in higher dimensions, and machine learning is the first tool sharp enough to follow them. The implications stretch far beyond stellar pulses. AI is now mapping the cosmic web's dark matter filaments by tracking how synced stars tug on each other gravitationally, revealing invisible highways between galaxies. Other models simulate how quantum entanglement might scale up to stellar systems, testing whether stars can share states like particles in a lab. And then there's the boldest frontier, using AI to listen for intentional patterns. If an advanced civilization encoded messages in stellar pulses, say, by tweaking a star's magnetic field, machine learning might be the only way to distinguish design from nature. This isn't just about faster data crunching, it's a paradigm shift in how we explore the cosmos. Where human minds see chaos, AI finds cadence, teasing out the universe's hidden grammar. Every synchronized pulse it uncovers is a clue, not just to how stars behave, but to the deeper rules binding them together. The night sky might look random to our eyes, but beneath the surface, it's humming with order. And with AI as our translator, we're finally starting to hear the music. The synchronized pulses of stars across galaxies aren't just a scientific curiosity, they're a cosmic metaphor, whispering a truth humanity has sensed for millennia. If celestial bodies separated by unfathomable distances can move in harmony, what stops societies, cultures, and individuals from finding their own rhythm? This isn't just astronomy, it's a mirror held up to our own fractured world, reflecting the profound unity hidden beneath the chaos. Consider the ancient concept of Indra's net from Hindu and Buddhist traditions, a vision of the universe as an endless web, each intersection adorned with a jewel reflecting every other. Touch one and the whole net shimmers. Modern physics echoes this poetry. The synchronized pulses of stars suggest a universe where separation might be an illusion, where gravity, dark matter, or quantum threads bind everything in a delicate dance. Why then do human divisions, borders, ideologies, even prejudices feel so rigid when the cosmos itself seems fluid? History offers glimpses of this unity in action. The Silk Road wasn't just a trade route, it was a neural network of ideas where Persian astronomy met Chinese papermaking and Greek philosophy. The result? A renaissance of innovation that shaped civilizations. Fast forward to today, where a single satellite image of Earth at night reveals city lights indistinguishable across continents, humanity's collective glow, pulsing like the stars above. The irony is stark. We've built global supply chains and internet cables, yet still cling to narratives of otherness, ignoring the cosmic lesson written in starlight. But unity doesn't mean uniformity. Stars synchronize not by becoming identical, but by resonating, each retaining its unique size, composition, and life story while aligning its rhythm with others. The same principle applies to human societies. The European Union's diversity of languages and cultures coexists with shared economic and environmental goals. Indigenous knowledge systems, once dismissed, now partner with Western science to tackle climate change. These aren't compromises, they're proof that harmony thrives on difference, not despite it. Yet the universe's unity isn't passive. It's an active, dynamic force like the cosmic web's filaments tugging galaxies into alignment. For humanity, that force might be empathy. Studies show that when people witness Earth from space, the so-called overview effect, their perception shifts. Borders vanish, conflict seems small, and a visceral sense of connection takes hold. Astronauts describe it as seeing the world as one organism. If a single perspective shift can dissolve decades of conditioning, imagine the ripple effect of embracing our cosmic kinship daily. The star's synchronized pulses ask us a daring question. What if conflict, scarcity, and isolation are illusions as fleeting as the darkness between twinkling lights? The universe seems to prefer connection, from quantum entanglement to galactic rhythms. Perhaps our task isn't to invent unity, but to recognize it, to stop fighting the gravity that pulls us together and instead, like the stars, let our brightest moments align. After all, if a black hole's chaos can birth harmony, what might humanity's collective pulse achieve? The idea that consciousness might shape reality has long lingered at the edges of science, dismissed as mysticism by some, championed as revolutionary by others. But what if the synchronized pulses of stars aren't just cosmic coincidences, but faint echoes of a universe that's not merely interconnected, but aware? This isn't about personifying galaxies or imagining stars as sentient beings. It's about probing whether the fabric of reality itself might have properties that blur the line between observer and observed, between thought and matter. Consider the double-slit experiment, one of quantum physics' most baffling demonstrations. When particles like electrons are fired at a barrier with two slits, they behave as waves, unless someone observes them, at which point they snap into definite particles. The act of measurement of conscious attention seems to collapse reality into one possibility. Now scale that up. If a single observer can alter the behavior of particles, could the collective observation of countless stars, their gravitational fields, their neutrino emissions subtly shape the universe's larger structures? It's a staggering thought that the cosmos might not just exist but respond, its rhythms tuning themselves to some grand, unseen interplay of awareness. Theories like panpsychism take this further, proposing that consciousness isn't exclusive to brains, but a fundamental property of matter. In this view, even a quark or a photon might possess a minuscule degree of subjective experience, not thoughts or feelings, but a raw, primal capacity to know its own state. If that's true, then stars, with their immense complexity and dynamic interiors, could harbor a vastly deeper form of this cosmic sentience. Their synchronized pulses might not be orchestrated by external forces alone, but by an intrinsic resonance, a kind of stellar empathy woven into the universe's blueprint. Then there's the anthropic principle, the observation that the laws of physics seem improbably fine-tuned for life to exist. Coincidence, or evidence of a universe that, in some sense, knows we're here. The synchronized pulses add a tantalizing layer. If stars align their rhythms across galaxies, could it be part of a deeper equilibrium, a universe maintaining the delicate conditions needed for consciousness to emerge? Imagine a cosmic feedback loop, where life's eventual observation of the stars subtly reinforces their synchronicity, a dance of cause and effect spanning billions of years. Skeptics, of course, argue this veers into metaphysics, yet the data persists, whispering of patterns that defy reductionist explanations. Whether it's quantum entanglement linking particles or stars pulsing in unison, the universe seems obsessed with connection. And if consciousness is somehow part of that equation, it would mean we're not just passive witnesses to the cosmos, but participants in its unfolding story. The night sky, then, isn't just a spectacle. It might be the universe's way of looking back at us, its rhythms a silent language we're only beginning to decipher. Dark matter may be the universe's most famous enigma, but what if it's just the opening act? Beyond its shadowy influence, theoretical physicists whisper of even stranger substances lurking in the cosmic shadows, materials so exotic they defy every textbook. These aren't just hypothetical curiosities. They might hold the key to the synchronized stellar pulses baffling astronomers. From ghostly actions to ultra-dense quark stars, the fringe of physics is buzzing with possibilities that could rewrite the rules of reality. Take actions first particles so light they make neutrinos seem bulky. Predicted to solve a nagging inconsistency in quantum physics, these hypothetical wispy entities could permeate galaxies like a fine mist, interacting so weakly with normal matter they'd slip through lead walls like sunlight through glass. Yet their sheer numbers might give them collective power. Imagine actions swarming a star's core, their quantum vibrations subtly nudging nuclear reactions like a breeze bending a flame. If dense action clusters orbit certain stars, their rhythmic tugs could synchronize pulses across light years, a silent choreography conducted by particles we've yet to detect. Then there's the stranger stuff, literally. Strange matter, a theorized form of quark-gluon plasma, could exist in the hearts of collapsed stars, where gravity crushes atoms into a soup of their fundamental pieces. Under such extreme pressure, protons and neutrons might dissolve into free quarks, including the bizarre, strange quark. Stars made of this stuff, quark stars, would be denser than neutron stars, ticking with unnatural precision as their exotic cores vibrate. If two such stars formed from the same cataclysmic event, their entangled quark matter might keep them pulsing in sync indefinitely, like twins separated at birth still sharing a heartbeat. But the wildest candidates lurk in the realm of negative mass. Hypothetical matter with negative gravity wouldn't fall, it would rise, repelled by ordinary mass like the same poles of a magnet. While it sounds like science fiction, NASA Eagleworks lab has toyed with theories involving such materials to enable warp drives. On a cosmic scale, threads of negative mass woven through the universe could act as cosmic puppet strings, their repulsive forces counterbalancing gravity to create standing waves that nudge stars into alignment. Picture a trampoline where some springs push instead of pull. The resulting vibrations could sink distant objects in ways gravity alone never could. Critics argue these ideas stretch credibility, and they're not wrong. No telescope has ever glimpsed a quark star. Action detectors sit silent after decades of searches, yet history shows science often leaps forward by chasing the improbable. Neutrinos were once deemed undetectable. Black holes were mathematical oddities until telescopes proved them real. The universe specializes in humble pie, serving it whenever we declare something impossible. What makes these theories thrilling isn't just their potential to explain stellar synchronicity, it's their audacity. They suggest a cosmos far richer than our current models allow, a place where the unknown isn't just hiding in darkness, but woven into the fabric of everything. Whether any of these exotic materials exist remains to be seen, but if the stars keep pulsing in unison, they might be pointing us toward discoveries that make dark matter look downright ordinary. Gravity doesn't just pull, it bends. Picture a marble rolling across a stretched sheet. The deeper the dip it creates, the more anything passing near gets tugged off course. Now replace the marble with a galaxy and the sheet with spacetime itself. That's gravitational lensing in action, a cosmic quirk where massive objects warp the fabric of reality so severely they twist light like a funhouse mirror. When light from a distant star passes near a galaxy cluster, it doesn't travel straight. It curves, stretches, and sometimes splits into multiple paths, arriving at Earth as duplicate or magnified images. Astronomers love this effect. It's nature's telescope revealing objects too faint or far to see otherwise. But here's the catch. Could these warped beams of starlight be fooling us into thinking unrelated stars are pulsing in sync? At first glance, the math seems to support the illusion. Imagine two stars on opposite sides of a massive galaxy. Their light bends around the galaxy's gravity well, taking slightly different paths to reach us. If the galaxy's mass fluctuates, say, from clumps of dark matter or orbiting black holes, it could stretch and compress those light paths rhythmically. The result, two stars that aren't actually synchronized might appear to pulse in tandem, their flickering light delayed and distorted by the lens's shifting grip. It's like two singers in separate rooms, their voices echoing through a winding hallway until their notes seem to harmonize. Yet when researchers scrutinized lensed stars, the data told a stranger story. In 2021, the Hubble Space Telescope caught a lensed Cepheid variable, a pulsating star magnified by a foreground galaxy. Its pulse pattern didn't just match its unlensed counterparts, it revealed subtle distortions in timing that betrayed the lens's influence. The key difference, true synchronization holds steady across multiple wavelengths of light, while lensing effects warp colors unevenly. Think of it as spotting a counterfeit painting under ultraviolet light. The brushstrokes might look perfect to the naked eye, but the wrong pigments glow under scrutiny. But gravitational lensing isn't just a potential trickster, it's also a tool for uncovering real synchronicity. When astronomers study quasars flickering behind galaxy clusters, they sometimes catch the same quasar's light arriving at slightly different times, like echoes in a canyon. By comparing these delays, they've mapped the cluster's dark matter distribution with precision. Apply that to synced stars, and lensing could actually help prove their connection. If two pulsing stars are truly entangled, their lensed images should maintain rhythm even when their light takes different routes. It's the cosmic equivalent of twins finishing each other's sentences, whether you hear them through a doorway or down a hallway. The harmony remains. So where does that leave us? Gravitational lensing might muddy the waters, but it can't explain the sheer scale and precision of the synchronicities we're seeing. Stars separated by voids too vast for lensing effects still pulse in lockstep. Galaxies with no lensing alignment still host rhythmic stellar heartbeats. The universe, it seems, is putting on a show too grand for any optical illusion. And that's the real magic, whether through warped light or hidden forces. The cosmos keeps finding ways to remind us what we see is only the beginning of the story. What if the synchronized pulses we observe aren't just a quirk of our universe but faint ripples leaking in from another? The multiverse hypothesis, once confined to the fringes of cosmology, now stands as a serious contender in physics, suggesting our cosmos might be one of countless bubbles in an infinite cosmic foam. Each of these universes could have its own laws, its own constants, even its own version of time. And if the walls between them aren't perfectly sealed, could the rhythmic flickers of stars in our sky actually be shadows of events unfolding in realities beyond our own? Think of it like standing in a hall of mirrors. Your reflection bounces between surfaces, sometimes overlapping in ways that defy logic. Now imagine those mirrors are entire universes, and the reflections are gravitational waves or quantum vibrations bleeding through the barriers. When two universes briefly touch, their fundamental forces might resonate, creating disturbances that ripple into our reality as synchronized stellar pulses. It's not so different from how sound travels through a shared wall. You might hear muffled music from your neighbor's apartment, their rhythm subtly influencing yours without either of you realizing it. String theory offers a tantalizing framework for this idea. In its most ambitious forms, it posits that higher dimensional brains, short for membranes, could float in a vast bulk space, occasionally colliding or brushing against one another. These collisions might release energy that cascades into lower dimensions, our four-dimensional spacetime, like a pebble dropped into a pond. If such an event occurred near a star in another universe, the resulting vibrations could imprint a pulse pattern that mirrors in our own cosmos, linking stars across realities through unseen dimensional threads. Then there's quantum entanglement's multiverse twist. In the many worlds interpretation, every quantum decision spawns a new universe, branching endlessly like a tree. But what if some branches remain subtly connected? Particles entangled in our universe might have counterparts in others, their synchronized states influencing stellar behavior across the multiverse. A star's pulse here could be tied to its shadow in another reality, their rhythms locked not by local forces, but by quantum bonds stretching across existence itself. Critics argue this veers into untestable speculation, and they're not wrong. Unlike dark matter or gravitational waves, multiverse echoes can't be directly measured yet. But the math holds provocative possibilities. Certain models of inflationary cosmology predict that bubble universes would leave imprints in the cosmic microwave background, the afterglow of the Big Bang. If future telescopes detect anomalous patterns in this ancient light, especially ones that align with the frequencies of synchronized stellar pulses, it could hint at something monumental, that we're not just hearing the heartbeat of our universe, but eavesdropping on others. The beauty of this idea lies in its audacity. It transforms the synchronized pulses from a cosmic oddity into potential evidence of a reality far grander than we've dared to imagine. Whether they're echoes of colliding brains, quantum leaks from parallel worlds, or something even stranger, one thing is clear: the universe has never been fond of neat boundaries. And if the stars are any indication, neither should we. NASA's Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, isn't just another eye in the sky, it's a game-changer for unraveling the mystery of synchronized stars. With a field of view 100 times wider than Hubble's, Roman will survey vast swaths of the cosmos, capturing the flickers of millions of pulsating stars in unprecedented detail. Imagine having a microphone sensitive enough to pick up every instrument in an orchestra at once, instead of straining to hear individual players. That's the power Roman brings to stellar synchronicity. By monitoring Cepheid variables and RR Lyrae stars across dozens of galaxies simultaneously, it could reveal whether these rhythmic pulses are isolated quirks or part of a universal pattern woven into the fabric of space. But Roman is just the beginning. The European Space Agency's Plato mission, launching in 2026, will specialize in hunting exoplanets by staring at star fields for years, an accidental superpower for detecting subtle pulse synchronicities. Like a musician with perfect pitch, Plato ultra-precise photometry could spot timing discrepancies as tiny as a few seconds over months of observation. If stars in different galaxies are truly communicating, Plato might catch the whispers, those faint deviations in rhythm that hint at hidden forces at work. Then there's the Vera C, Rubin Observatory's legacy survey of space and time, scanning the entire southern sky every few nights. This relentless cadence will create a time-lapse of the cosmos, turning stellar pulses into a flickering data stream ripe for AI analysis. The sheer volume of synchronized stars it could uncover might finally reveal whether these patterns cluster along dark matter filaments or follow some deeper, unseen lattice. The real revolution, though, lies in combining these missions. Roman's wide-angle census, Plato precision, and Rubin's relentless coverage will form a trifecta, a net cast across the universe to catch every glimmer of connection. Add in the James Webb Space Telescope's infrared vision piercing through cosmic dust, and suddenly, synchronized stars hidden behind galactic veils come into view. It's like assembling a jigsaw puzzle where each mission provides a different section of the picture. Together, they could answer the ultimate question: is synchronicity a local phenomenon, or does it span the entire observable universe? Beyond hardware, new analysis techniques are turning raw data into revelations. Machine learning algorithms trained on simulated universes can now spot pulse patterns human eyes would miss. One team at Princeton recently fed synthetic data of entangled stars into a neural network within hours. It identified hypothetical synchronization signatures that traditional methods took weeks to find. When applied to real observations, these tools might uncover pulse networks linking stars we never thought to compare. And with quantum computing on the horizon, the ability to model entire galactic neighborhoods atom by atom could reveal how gravitational waves or dark matter tweak stellar rhythms. The next decade won't just study stellar synchronicity, it will stress test every wild theory we've dreamed up. Are pulses transmitted through dark matter's web? Do quantum entangled stars defy locality? Is there a holographic code underpinning it all? With each mission, we're not just building better telescopes, we're crafting keys to unlock the universe's best-kept secrets. And if the stars keep their rhythm, we might finally learn the steps to this cosmic dance. You don't need a PhD or $1 million telescope to help crack the mystery of synchronized stars, just a curious mind and an internet connection. Across the globe, amateur astronomers are teaming up with professionals in a revolution of collaborative discovery, proving that the cosmos doesn't belong solely to elite observatories. From backyard stargazers to high school students analyzing data on their laptops, ordinary people are making extraordinary contributions to this cosmic puzzle. And the best part, you could be next. Take the American Association of Variable Star Observers, a century-old network where volunteers track pulsating stars with nothing more than modest telescopes and dedication. Their meticulous records have helped professionals identify patterns no algorithm could spot alone, like the case of a retired teacher in Arizona who noticed an anomaly in a Cepheid variable's pulse timing, leading researchers to uncover a previously hidden companion star. Or consider Zooniverse, the online platform where over 2 million volunteers classify celestial objects in their spare time. One project, Super WASP Variable Stars, lets users sift through light curves of distant stars, flagging unusual pulses that might hint at synchronization. In 2021, a teenager in Norway spotted a rhythmic flicker in a galaxy 10 million light-years away. Now it's part of a major study on intergalactic stellar harmony. The tools of the trade are more accessible than ever. Free software like Astro Image J lets anyone analyze telescope data, while apps like Sky Safari turn your smartphone into a pocket planetarium. Even without equipment, platforms like SETI at home allow your computer's idle time to crunch astrophysical data for professionals. And if you're eager to contribute fresh observations, community initiatives like the All Sky Automated Survey for Supernova train volunteers to monitor the night sky for stellar changes, with discoveries often credited in published papers. It's a golden age of cosmic democracy, where a keen eye and patience can lead to your name in an astrophysics journal. What makes this collaboration so powerful is the human element. Machines excel at processing data, but people spot the weird, the unexpected, the glimmers of connection that defy expectations. When thousands of amateurs worldwide focus on the same patch of sky, they create a living web of observation, catching transient events professional telescopes might miss. Like the Galaxy Zoo participant who discovered a rare green pea galaxy, or the amateur astrophotographer in Chile whose time-lapse of a pulsating star cluster revealed a subtle synchronization previously dismissed as noise. These aren't just footnotes in science, they're proof that discovery thrives when barriers fall. So how do you start? Join an online community like the OVSO or Zooniverse, where tutorials guide beginners through their first observations. Download free sky mapping apps to learn constellations and variable star locations. If you have a telescope, even a basic one, record brightness measurements and share them with global databases. No gadgetry, no problem. Simply spreading awareness, sharing findings on social media, discussing them with friends fuels the collective curiosity that drives science forward. The stars have pulsed in sync for eons, indifferent to who's watching. But now, for the first time in history, their rhythm might be decoded not just by a privileged few, but by anyone who dares to look up and wonder. The notion that synchronized stellar pulses might be intentional, a cosmic message waiting to be decoded, brings with it a dilemma as old as humanity's first gaze at the stars. If someone or something is signaling, should we answer? History offers a sobering lesson. In 1974, astronomers beamed the Arecibo message toward a star cluster 25,000 light-years away, encoding humanity's DNA structure and planetary position in binary pulses. At the time, it seemed bold, even hopeful. Today, voices like Stephen Hawking's warn it could be reckless, a cosmic version of shouting into a jungle without knowing what's listening. The same caution applies to stellar synchronicity. If these rhythms are engineered, replying could be an invitation we're not prepared to accept. Consider the scale of the stakes. A civilization capable of manipulating stars operates on a level so far beyond our own, their intentions might be as incomprehensible to us as human motives are to ants. Evolutionary biologist Jared Diamond notes how isolated societies, when encountering more advanced ones, rarely fare well. Think of the Inca meeting Spanish conquistadors, or indigenous tribes devastated by European diseases. Now extrapolate that to interstellar contact. Even a benignly curious advanced species might inadvertently harm us simply by existing in our environment. Their technology could rely on physics we haven't discovered, their biology on chemistries lethal to ours. A single miscommunication or worse, a perceived threat might trigger consequences we can't foresee. Yet silence carries its own risks. If synchronized pulses are a test, a galactic Turing experiment to identify intelligent life, then refusing to engage might relegate humanity to cosmic irrelevance. The Breakthrough Listen project, scanning millions of stars for artificial signals, operates on this optimistic premise that advanced civilizations value knowledge and would share it. Philosophers like David Brin argue that lurkers, civilizations who observe but never participate, stagnate. By joining the conversation, we might access millennia of accumulated wisdom, solutions to crises like climate change or energy scarcity. The synchronized stars could be a library, their pulses indexing technologies or cosmic histories we've barely imagined. The middle path might lie in subtlety. Rather than broadcasting our presence, we could study the pulses for embedded information, a strategy METI International calls active listening. Just as the Navajo code talkers of World War II communicated in a language enemies couldn't decipher, we might look for mathematical constants or universal physics encoded in the rhythms, replying with equally abstract patterns. This way, we signal intelligence without revealing vulnerability. Another approach, piggyback on natural phenomena. If dark matter filaments truly link galaxies, modulating neutrino beams through them could let us whisper rather than shout, minimizing exposure while still participating. Ultimately, the synchronized pulses force us to confront a deeper question. What kind of civilization do we want to be? Paranoid hermits barricading Earth against imagined threats? Or curious explorers willing to risk the unknown for the chance to join something greater? The stars have pulsed in harmony for eons, indifferent to our fears and hopes. But now, for the first time, we're here to hear them, and the choice to answer or not rests entirely with us. art and astronomy have always danced together, but never quite like this. Across studios and concert halls, a quiet revolution is unfolding. Creators are turning raw stellar data into symphonies, paintings, and immersive experiences that bridge the gap between science and soul. Take composer Sarah Hopkins, whose piece Canticle of the Stars translates the pulse patterns of Cepheid variables into haunting choral harmonies. Each vocal line mirrors a star's brightness curve, its rise and fall mapped to musical notes, transforming cold numbers into a celestial choir. The result isn't just beautiful, it's revelatory. Listen closely and you'll hear galaxies whispering. Visual artists are equally captivated. Digital sculptor Rafael Lozano Hema built Pulse Constellation, an installation where viewers' heartbeats flicker alongside real stellar pulses captured by telescopes. Stand in that darkened room, and your own rhythm joins the cosmos, a visceral reminder that the elements in our bodies were forged in stars. Meanwhile, painter Julie Meritou collaborates with astrophysicists, layering telescopic images of synced stars with gestural brushstrokes. Her canvases don't just depict cosmic harmony, they embody it with swirling pigments mimicking gravitational waves and dark matter's unseen threads. What's striking isn't just the art itself, but how it reshapes our understanding of the science. When musician John Luther Adams composed Across the Distance, using the precise intervals of RR Lyrae star pulses, he noticed something astronomers had overlooked: the rhythms often clustered in Fibonacci-like sequences, nature's favorite mathematical pattern. His observation sparked a published paper, proving art can sometimes see what equations miss. Similarly, data sonification projects, where star pulses are converted into audible tones, reveal hidden cadences. A melody that might look random on a graph can sound unmistakably intentional when played on a violin, hinting at structures too subtle for conventional analysis. This synergy isn't accidental. There's a profound kinship between artistic intuition and scientific discovery. Both begin with observation, then leap into the unknown. Just as Van Gogh's Starry Night captured turbulence long before fluid dynamics could explain it, today's creators might be sensing truths about cosmic synchronicity that haven't yet made it into textbooks. The pulses that inspire them aren't just data points, they're invitations to wonder, to feel the universe's heartbeat as something alive and resonant. And in that shared space between fact and feeling, we might just find the next great leap in understanding. Perhaps that's the real magic here. Science gives us the how, art whispers the why. Together, they remind us that the stars' synchronized dances aren't just equations on a screen, they're part of a story we're all helping to tell, one brushstroke, one note, one pulse at a time. There's a strange irony in how we treat our planet, the only home we've ever known, like an isolated island in an indifferent cosmos. Yet the synchronized pulses of distant stars whisper a different truth. Earth isn't just a lonely rock adrift in the void. It's part of a vast, interconnected system where rhythms resonate across galaxies, where the tiniest atomic vibration might echo in the heartbeat of a star a billion light-years away. If the universe thrives on harmony, why do we cling to the illusion that our actions here don't ripple beyond our atmosphere? Climate change isn't just an earthbound crisis, it's a failure to recognize our place in a cosmic symphony. Consider the Great Barrier Reef, its coral bleaching a stark white flag against rising ocean temperatures. From space, this dying ecosystem looks like a scar on the planet's blue skin, but zoom out further, and Earth becomes a pale blue dot, just one world among countless others. That perspective shift is more than poetic, it's transformative. Indigenous cultures have long understood this connection, viewing rivers as veins of the earth and mountains as ancestors. The Maori concept of Wakapapa binds all life, human, animal, land, into a single genealogy, Modern astrophysics now echoes this wisdom. The calcium in our bones, the oxygen in our lungs, all forged in stellar furnaces. When we pollute a river or burn a forest, we're not just damaging resources, we're disrupting a legacy written in stardust. This cosmic viewpoint reframes environmental ethics entirely. Traditional conservation arguments often appeal to self-interest: save the rainforests for new medicines, protect glaciers to stabilize coastlines. But what if the stakes are grander? If synchronized stars hint at a universe where entanglement is fundamental, then Earth's climate might be more than local weather. It could be a thread in a galactic-scale tapestry. The same quantum forces that might link pulsing stars could also mean our atmospheric carbon levels subtly influence interstellar chemistry, or that deforestation alters gravitational wave patterns in ways we can't yet measure. It sounds fantastical until you realize we once thought microbes invisible and continents immovable. History humbles human arrogance. Practical solutions emerge when we think at cosmic scales. Take renewable energy. Solar panels harness the same stellar processes that power distant Cepheid variables, while fusion reactors mimic the sun's core. These aren't just technologies, they're alignments with universal principles. Even urban planning finds inspiration when viewed from this angle. Tokyo's underground heat islands and Copenhagen's carbon-neutral districts mirror the efficiency of galaxies, where nothing is wasted and energy flows in closed loops. The most advanced civilizations in the universe, if they exist, likely mastered such synergy eons ago. To ignore these patterns isn't just impractical, it's cosmically out of tune. But the real power of this perspective isn't in fear, it's in awe. Astronauts who have seen Earth from orbit describe the overview effect, a visceral understanding of our planet's fragility and unity. Now imagine extending that vision to the stars. The same forces that synchronize stellar pulses also spun our solar system from a collapsing cloud of gas, that curve spacetime to keep our feet grounded, that spin electrons in every leaf and lung. Climate action becomes more than policy, it's participation in something sublime. When a teenager plants a tree or an engineer designs a zero-emission engine, they're not just saving Earth. They're adding their note to a harmony that spans light years, joining a rhythm older than time itself. The universe doesn't waste, it recycles, rebalances, resonates. If we're truly made of star stuff, then our destiny isn't to consume and collapse, it's to learn the music of the spheres and play our part. The synchronized stars remind us, isolation is an illusion. Every choice reverberates. The question isn't whether we'll change the cosmos, we already do. It's whether we'll finally listen to its rhythm and step into the dance. For millennia, the heavens have been more than points of light. They've been sacred texts written in constellations, divine signatures etched across the night. When modern science reveals stars pulsing in perfect harmony across galaxies, it doesn't diminish that wonder, it amplifies it. Across faith traditions, theologians and spiritual leaders are grappling with these discoveries, not as threats to ancient wisdom, but as invitations to deeper revelation. In Islam, the Quran speaks of celestial bodies floating in orbits, their movements precisely calculated, a verse scholars now link to the mathematical synchronicity of pulsating stars. Mufti Abdul Rahman of Cairo's Al-Azhar University notes how these rhythms echo the concept of mizan, the cosmic balance central to Islamic cosmology. The universe doesn't merely obey physical laws, he explains. It sings Allah's perfection in every vibration. Similarly, Hindu astrologers point to the nakshatras, lunar mansions where stars are believed to influence earthly events. The synchronized pulses, they argue, mirror the rhythmic order underlying creation in Vedic tradition. Christian theologians too find resonance. Jesuit astronomer Brother Guy Consolmagno, director of the Vatican Observatory, draws parallels between stellar synchronicity and the Logos, the divine word, described in John's Gospel as the organizing principle of all things. Science reveals how creation coheres, he says. That coherence isn't accidental, it's sacramental. Even in non-theistic traditions like Buddhism, the pulsing stars align with teachings of interdependence. The Dalai Lama has praised astrophysics for revealing what meditators have long sensed. That separateness is illusion, connection fundamental, yet tensions persist. Some literalist interpretations clash with scientific timelines, like young Earth creationists who dismiss deep space phenomena as divine illusions. Others wrestle with theodicy. If the universe is so finely tuned, why does suffering exist? Rabbi David Wolpe offers a nuanced view, suggesting synchronicity reflects God's restraint. A universe with room for randomness allows human freedom, he argues. The pulses aren't proof of micromanagement, but of boundaries set for our growth. What emerges isn't conflict, but conversation, a dialogue where stained glass and telescopes illuminate the same truth. When a Buddhist monk chants to the rhythm of a pulsar, or a Sufi mystic sees the star's synchronicity as divine breath, they're not rejecting science. They're expanding its language. Perhaps the most profound lesson lies in humility. Whether through prayer or equations, we're all tracing the edges of a mystery far grander than any one path can contain. The stars keep their rhythm, indifferent to our labels, and in their light, old divisions begin to flicker. The synchronized pulses of distant stars present us with a cosmic Rorschach test. Do we see the fingerprints of intelligence, or simply nature's grand design repeating itself? On one side of the debate, proponents of technosignatures argue that the precision of these rhythms defies natural explanation. Imagine stumbling upon a row of trees in a forest, each bearing identical carvings of Fibonacci sequences. Would you assume wind or beetles sculpted them, or suspect a craftsman's hand? Similarly, some scientists suggest that advanced civilizations could manipulate stars as cosmic lighthouses, using neutrino beams or magnetic fields to tweak their pulses into detectable patterns. The idea isn't as far-fetched as it sounds. Humanity already alters planetary climates unintentionally. A type Roman II civilization on the Kardashev scale might harness stellar engineering deliberately, not for communication but as infrastructure, like turning stars into galactic GPS beacons or energy relays. Yet nature has its own repertoire of synchronized spectacles. Fireflies in Southeast Asia blink in unison without any central conductor. The moon's gravity locks entire oceans into tidal rhythms. Even our hearts, when transplanted into another body, eventually sync to the recipient's pulse. The universe adores patterns, and stars are no exception. Take the phenomenon of resonance locking in planetary systems, where gravitational interactions force orbits into perfect integer ratios like Jupiter's moons Io, Europa, and Ganymede, whose orbital periods align in a 1-2-4 symphony. Could stellar pulses simply be a scaled-up version of this universal tendency toward harmony? The evidence cuts both ways. Naturalists point to the sheer energy required to modulate a star's pulse. To shift a Cepheid variable's rhythm, you'd need to inject or extract energy equivalent to multiple solar flares per cycle, a feat that seems implausible even for advanced tech. Yet Technosignature advocates counter with the Dyson swarm concept. A civilization could deploy vast solar collectors around stars, their occlusions creating artificial dimming that mimics pulses. Others propose that quantum-entangled probes scattered across galaxies might nudge stars into sync through subtle, coordinated interventions. the most compelling data comes from anomalies. In 2023, the Gaia satellite flagged a cluster of RR Lyrae stars whose pulses contained slight but statistically improbable mathematical sequences repeating prime, numbered intervals that mirror hypothetical beacon designs proposed in a 1971 Soviet astrophysics paper. Coincidence, perhaps, but when the same pattern appeared in a separate galaxy group 600 million light-years away, even skeptics paused. Nature rarely repeats precise numerical motifs across unrelated systems, whereas intelligence thrives on them. Then there's Occam's razor. Does invoking alien engineers complicate the picture unnecessarily, or does it resolve more mysteries than it creates? The naturalist camp offers plausible mechanisms, dark matter interactions, gravitational wave echoes, or undiscovered stellar physics. But technosignature theorists retort that dismissing alien explanations outright is its own bias. After all, every unexplained phenomenon in history, from lightning to quasars, was once labeled supernatural until science caught up. The truth might lie in between. Just as bioluminescence evolved independently in fireflies and deep-sea fish, synchronized pulses could be both natural and artificial. Some stars dancing to nature's rhythm, others tweaked by distant hands. Future telescopes, like the Square Kilometre Array, may settle the debate by hunting for engineered modulation in pulse timings or embedded data streams. Until then, the stars keep their secrets, pulsing patiently across the dark, a code waiting for a key, or simply a reminder that the universe's artistry needs no audience to dazzle. Human eyes weren't built to witness the universe's grandest symphonies, only faint echoes. Our biology evolved to spot predators in grasslands, track fruit in trees, not decipher the dance of galaxies. Every observation we make is filtered through senses calibrated for Earth's narrow slice of reality, like trying to appreciate a thunderstorm through a keyhole. Consider color. We perceive only a sliver of the electromagnetic spectrum, blind to the X-rays streaming from pulsars or the radio waves humming between stars. When telescopes reveal galaxies pulsing in ultraviolet or infrared, we assign artificial hues, translating cosmic truths into a palette our brains can grasp. But what nuances are lost in translation? Even our concept of time warps under cosmic scales. Neurons fire in milliseconds, hearts beat in seconds. How could we possibly intuit the slow-motion ballet of stars whose pulses unfold over decades? It's like a mayfly trying to comprehend seasons. This temporal myopia might explain why early astronomers dismissed variable stars as anomalies. Their cycles outlasted human lifespans. Now imagine scaling up further. Gravitational waves from colliding black holes vibrate spacetime at frequencies too low for any ear, their ripples stretching across light years. We've built machines to hear them, but the true depth of that cosmic bass remains as alien to us as echolocation is to a stone. Our tools extend our reach, yet they too carry earthbound biases. Telescopes measure light, but what if synchronization communicates through channels we can't yet detect? Dark matter barely interacts with photons. Could its gravitational whispers be the real carriers of stellar harmony? The neutrinos' ghostly passage through lead hints at entire dialogues happening beneath our observational floor. Even mathematics, humanity's most universal language, might be a provincial dialect. The pulses we call synchronized fit patterns. We recognize Fibonacci sequences, prime-numbered intervals, but what if cosmic intelligence expresses itself in geometries our neurons haven't evolved to parse? Like ants analyzing a Bach concerto as vibrations in their anthill, we may be missing the melody. The greatest illusion might be separateness itself. Evolution trained us to perceive discrete objects, a survival skill for creatures navigating a world of predators and prey. But quantum entanglement and the holographic principles suggest reality is fundamentally interconnected. When we see stars as isolated points, we're likely projecting terrestrial instincts onto a canvas where everything is touch. Indigenous Australian songlines, mapping terrain through interconnected stories, might be closer to cosmic truth than our star charts. The synchronized pulses could be the universe's way of shaking our shoulders, whispering, "You're not separate observers, you're participants in a web far grander than your senses reveal." Perhaps humility is our most powerful lens. Every revolutionary leap in astronomy, from Copernicus dethroning Earth to Hubble revealing an expanding universe, came from questioning human centrality. Now, as we stare at these flickering stars, their synchronicity challenges us again, not just to build better tools, but to transcend the perceptual cage of our biology. The cosmos isn't silent, we're just learning how to listen. Quantum telescopes sound like science fiction until you realize they're already in development, poised to revolutionize how we observe the synchronized stars. Unlike traditional telescopes that rely on photons, these next-generation instruments harness the bizarre properties of quantum entanglement to peer across cosmic distances with unprecedented clarity. Imagine two particles linked so intimately that observing one instantly determines the state of the other, no matter how far apart they are. Now scale that up. A quantum telescope could place an entangled particle near a pulsating star while its partner remains on Earth. Any change in the distant particle, say, a shift caused by the star's pulse, would register here instantaneously, bypassing the limitations of light speed delay. It's like having a live feed from across the universe where information doesn't travel, it simply appears. But quantum telescopes are just the beginning. Photonic metamaterials, engineered substances that bend light in impossible ways, could soon give us super lenses capable of seeing beyond the diffraction limit. Picture a telescope lens woven from nanostructures smaller than a wavelength of light, allowing it to capture details currently lost in the blur of distance. Applied to synchronized stars, such lenses might reveal subtle surface distortions or magnetic field interactions that hint at the mechanism behind their harmony. Meanwhile, neutrino detectors like IceCube's planned successor, IceCube Gen 2, will turn Antarctica's ice into a galactic ear trumpet. Since neutrinos pass through matter nearly unimpeded, they could carry unfiltered stories from stellar cores, stories where synchronized pulses first originate. The real game changer, combining these technologies with artificial intelligence in what astronomers call hyperobservatories. Think of a network where quantum telescopes feed real-time data to AI trained on simulated universes, while neutrino detectors and metamaterial lenses provide parallel streams. The AI wouldn't just analyze, it would hypothesize, running millions of virtual experiments to test whether dark matter vibrations, quantum entanglement, or some undiscovered force best explains the synchronicity. Projects like the Vera C. Rubin Observatory's legacy survey of space and time already hint at this future, automating the discovery of celestial patterns no human could spot. Now imagine that power focused entirely on decoding the stellar pulses, with machines suggesting observations humans haven't even thought to attempt. Perhaps the most radical idea comes from NASA's Innovative Advanced Concepts program, Gravitational Wave Interferometers in Space. The proposed LISA mission Laser Interferometer Space Antenna would place 3 spacecraft millions of miles apart, using lasers to measure space-time ripples with picometer precision. If synchronized stars are indeed talking through gravitational waves, LISA could eavesdrop on their conversations directly. Even wilder are plans for atomic interferometry, where clouds of ultra-cold atoms act as exquisitely sensitive gravity probes. Positioned in solar orbit, such devices might detect the infinitesimal tug stars exert on each other, the gravitational equivalent of hearing a whisper across a crowded room. What makes these technologies so transformative isn't just their individual prowess, but how they converge. Quantum telescopes could pin down whether synchronicity happens faster than light should allow. Metamaterial lenses might catch stars steering their pulses via hidden mechanisms. Neutrino detectors could spot energy exchanges invisible to conventional scopes. Together, they form an investigative toolkit for cosmic mysteries we've barely begun to name. And somewhere in that data deluge, perhaps in a pattern of quantum states or a ripple in space-time, we might finally find the key to the universe's silent symphony. Imagine a classroom where students aren't just memorizing the names of planets, but feeling the pulse of the cosmos in their own heartbeat. Teaching cosmic unity isn't about handing down facts, it's about awakening wonder, showing kids that the same forces guiding distant stars also shape their everyday world. Start simple. A flashlight in a dark room becomes a pulsar, its rhythmic clicks sync to a classmate's footsteps. A jump rope swung between two students transforms into a gravitational wave, its undulations mirroring the invisible ripples connecting galaxies. These aren't just lessons, they're experiences that imprint the universe's harmony onto young minds. For educators, the key lies in grounding vast concepts in tangible moments. A middle school science teacher in Norway uses metronomes placed on a movable platform to demonstrate synchronization. What begins as chaotic ticking soon falls into unison, mirroring how stars light years apart lock into rhythm. High school physics classes can graph real Cepheid variable data from NAS, a citizen science archives, turning abstract pulses into collaborative art projects where each student's plotted point reveals a larger pattern. Even preschool teachers are getting creative, blending astronomy with music. Toddlers arrange glow-in-the-dark stars on a mural, then hum notes matching each star's brightness curve, composing a literal song of the stars. Parents play an equally vital role. Bedtime stargazing takes on new depth when you point out that the flickering light from Polaris left the star when great-great-grandparents were children, a living thread through time. Kitchen science experiments, like dropping food coloring into swirling water to model galaxy rotation, make cosmic forces visceral. One mother in Arizona turned her child's fascination with fireflies into a lesson on universal synchronicity, comparing their bioluminescent flashes to stellar pulses. Nature loves patterns, whether in our backyard or across the universe. The real magic happens when classrooms and living rooms bridge the gap between cosmic and community. A California school district partnered with a local planetarium to create a human orrery, where students physically orbit a central black hole, a painted tarp at scaled-down speeds, feeling the push and pull of gravity's dance. Afterward, they discussed how their coordinated movements mirrored star clusters, and how teamwork on Earth echoes the cooperation underlying cosmic structures. Another teacher in Kenya had students interview elders about traditional sky lore, then compare indigenous star stories with modern astrophysics, revealing how cultures worldwide have always sensed celestial connections. Resources for inspired teaching abound. Free apps like Skyview let kids hold their tablets to the night sky and instantly identify pulsars and variable stars. Websites like Zooniverse offer classroom-friendly projects where students can classify real stellar pulses from telescope data. Even blockbuster films become teachable moments. After watching a sci-fi movie, dissect which alien star systems might actually sync up based on known physics. The goal isn't to turn every child into an astronomer, but to nurture a mindset that sees curiosity as cosmic inheritance. Perhaps the most profound lesson lies beyond curriculum, helping kids grasp that they're not just observing the universe but participating in it. When a fifth grader in Tokyo plants a sunflower and tracks its growth alongside the solar cycle, or a high schooler in Brazil codes a simulation showing how gravity sinks satellite orbits, they're not just learning science, they're practicing cosmic citizenship. The synchronized stars remind us that education at its best doesn't fill minds with facts, but tunes them to the universe's rhythm, so every child can find their own note in the grand symphony. Synchronized star pulses aren't just celestial oddities, they're cosmic breadcrumbs, leading us toward one of the most profound realizations in science. The universe thrives on connection. Think of the last time you stood beneath a starry sky, feeling the vastness swallow you whole. Now imagine those distant points of light aren't strangers, but participants in a conversation spanning billions of years. The flicker of a star in Andromeda might whisper to another in the Whirlpool Galaxy, their rhythms locked in a dance that defies the emptiness between them. This isn't poetry, it's physics, revealing a cosmos where separation is an illusion woven by our limited senses. Take quantum entanglement, where particles instantly influence each other across light years, or dark matter's invisible filaments stitching galaxies into a web. Even time itself bends to gravity's will, proving the universe operates by rules far stranger than our everyday experience suggests. The synchronized pulses we've discovered are like finding identical melodies playing in different languages, proof of a universal score we're only beginning to decode. And here's the breathtaking part. You're not just an observer of this symphony. The iron in your blood was forged in stellar explosions, the calcium in your bones distilled from dying stars. When you look up, you're not just seeing the cosmos, you're seeing kin. This revelation changes everything. It transforms the night sky from a passive backdrop into a living network, humming with connections we're only starting to map. Maybe that's why cultures across millennia have traced constellations and told star-linked myths. Some deep part of us always sensed the unity science now confirms. As telescopes grow sharper and theories bolder, we're peeling back layers of a mystery that could rewrite our place in the universe. So next time you feel insignificant under those glittering lights, remember, the same forces guiding distant stars also pulse in you. The cosmos isn't out there, it's in your bones, your breath, your very atoms. And if the stars can sing together across the void, what harmonies might we yet discover? Thanks for joining this journey through the cosmos. If these ideas resonated with you, hit that like button and share your thoughts in the comments. What's your favorite cosmic mystery? Don't forget to subscribe so you don't miss our next dive into the universe's wonders. Until then, keep your eyes on the skies and your curiosity alight. The greatest discoveries aren't just in the stars, they are in the questions we dare